I figure I'll actually start on time tonight, so hopefully we can get out of here a few minutes early and everyone can get home and put the turkey in. Thanks to all of you who made it, and curses to everyone who didn't. We heard at least the traffic wasn't too bad on the bridge. So this is going to be two parts tonight. I'm going to talk about the role of DARPA, the Defense Advanced Research Projects Agency, and then Kate is going to talk about women in computing. And I'm going to go probably only 20 minutes, so we'll segue into Kate and then take a break and sometime middle of her part, and depending on how long it goes. So the reason for talking about DARPA is that they're responsible for a large proportion of the history of computing that you've heard about. Time sharing, certainly workstations, computer graphics, networking. And so this agency has been so essential to supporting the great computing research since the middle 1960s that it's important to talk about them a little bit. This is a picture that you can't possibly read on the screen. It's called the tire, and I'll explain it to you. You don't have to read it. It's called the tire tracks diagram because the original black and white version of this, the line that's green here was a set of horizontal lines that looked like somebody had driven across the page. It was really terrible graphics. And let me just describe what this shows, even though you can't read it. It shows 19 different billion-dollar or greater subsectors of the IT industry, although some of them are sort of dead now. But there's time sharing, client-server computing, graphics, entertainment, meaning video games and animation, the internet, local area networks, workstations, GUIs, integrated circuit design techniques, reduced instruction set processors, may they rest in peace, relational databases, parallel databases, data mining, parallel computing, RAID arrays, disk arrays, portable communication, meaning wireless, the web, speech recognition, broadband last mile, so things like DSL. Right? And what this picture shows for each of those, let me get rid of the mess I've just made, is 4 different lines. The red line is university research. The blue line is, wait a sec, that's a bad example. Yeah. The blue line is industry R&D. The dotted line is product introduction, right? And the green line is when it became $1 billion sector. All right? And those of you who were with us 2 years ago have seen at least the black and white version of this picture. Right? So that's the basic idea. And then there are a whole bunch of things that are sort of buried in this picture. For example, every one of these $19 billion sectors shows both the stamp of federally funded university-based research and of corporate R&D. There's no one of them that resulted exclusively from one or the other. I think that's correct. Right? Secondly, there's a lot of interplay between them, and I'll give you some DARPA examples of that, but you see these lines sort of running from time sharing to the internet, from graphics to workstations, from integrated circuit design to RISC processors, but integrated circuit design should actually go up to graphics as well in a way that I'll describe in a second. Okay, so there's lots of interplay among these things. Third, a discouraging aspect of this is it tends to take 10 or 15 years for an idea to become $1 billion industry. Over the decades, we've never managed to make that go faster. All right? So that's not necessarily product introduction to $1 billion industry, but the ideas that product introductions are based on. At the time that sector becomes worth $1 billion, the basic ideas are 10 or 15 years old. Right? Another important point is there's no linear pipeline from university research to industry R&D to products. It sort of goes back and forth, and it depends on the particular area. But for example, if you look at reduced instruction set processors, Burton Smith said that reduced instruction set RISC had Seymour Cray's name in it, okay, because the original CDC machines were RISC machines. Even setting that aside, it's absolutely clear that modern RISCs were invented by IBM, right? And IBM decided it didn't make sense to pursue them and dropped it. And the reason, something we talked about in the IT policy course, is you probably read this book called The Innovator's Dilemma. right? You know, it's very hard for a company to pursue something that's going to kill its cash cow, right? And IBM was doing perfectly well with its existing large-scale complex instruction set processors. So was Digital Equipment Corporation, okay? So they weren't the people who picked up risk. IBM dropped it. Berkeley and Stanford, David Patterson at Berkeley and John Hennessy at Stanford, picked it up in the SPUR project at Berkeley and the MIPS project at Stanford, right? And SPUR became the Sun SPARC processor, and MIPS became Hennessy's startup, MIPS Computer Company, whose processors then went on into SGI and DEC and a bunch of places like that. But then IBM got back in the business, picking up where they and Berkeley and Stanford had left off, and became one of the biggest designers and manufacturers of reduced instruction set processors. All right, so if you look at risk here, it's industry R&D up to universities, down into products, and those products, you can't quite read this, are Sun, SGI, IBM, and HP, right? And eventually became a billion-dollar industry. Right, so there's a huge amount buried in this. Let me see if I've skipped anything. 19 subsectors, the various types of activity, flows within the subsectors and within subsectors. Lots of back and forth in between. Subset of the contributors. Every subsector bears the stamp of federally funded university research and industry R&D. Lots of interplay. It's not a pipeline. Takes 10 or 15 years, and lots of research interactions across subfields. Right? And again, when we come back to some DARPA examples, I'll talk more specifically about that. And then there are a set of concepts that aren't directly illustrated by this picture, but are described in the report that the picture is stolen from. And let me just touch on these briefly. One is that unanticipated results are often as important as anticipated results. Okay, so you know, time sharing was designed to share these very expensive machines, and somebody came up with email and chat, right? And probably email is much more important, a legacy of the work on time sharing systems than time sharing systems themselves, which nobody uses anymore. Right? And there are lots of other examples of that. You never know what the next big hit is going to be. It's hard to tell which of these are going to become billion-dollar sectors. And my example of that, which I won't go through in any detail, is that this colored picture was actually a 2003 or 2004 rehash of a report that a set of us did in 1995. And in 1995, we had about 10 things on our picture. And as we were doing that picture, this is for a National Academy study of sort of IT innovation, we were crying in our beer in the evening because none of us could figure out what the next big thing was going to be. So this was the standard, woe is me, computer science is dead, there's nothing interesting going on. Right? Wow. And then when we redid the report 8 years later, there were another 10 things that we had completely missed. For example, the original report done in 1993 or 94, we had no idea the web was going to be big. Right? We had no idea broadband last mile was going to be big. Cell phones were these enormous bricks that rich people had, rich people with big belts. Okay? And, you know, this sort of stuff. Okay, so we missed a whole bunch of things that 8 years later were billion-dollar sectors. And similarly, as we were doing the rehash in 2003 or 2004, we couldn't figure out what was going to be next. But there's going to be something. You just don't know what it is. If you did know what it is, we'd all be, you know, rich. So that's the story. You know, lots of times research puts ideas in the storehouse that gets pulled out later. So, for example, if you want to do e-commerce, you got to have the internet, you got to have the web, you got to have public key cryptography for secure credit card transactions, you got to have high-performance back-end transaction servers. All of those things get drawn together to allow you to build an e-commerce site. And when you go to build an e-commerce site, you've got all the pieces you need, and it's a simple matter of engineering. That doesn't mean it's really simple, but in some sense what you're doing is the difficult job of engineering a new capability out of a bunch of ideas that are there. You know, one of the attributes of university research as opposed to industry R&D is it trains people. And that's important to keep in mind. Right? So the biggest reason that tech economies grow up around universities has nothing to do with tech transfer. It has to do with the graduates. Right? It's the people. University and industry research tend to be complementary, You know, Microsoft research is an exception. But again, something we talked about in the IT and public policy course, and I won't belabor tonight, is if you think of Microsoft's overall R&D budget, which is, I don't know what it is these days, probably 10 billion. Sorry?
6 billion.
6 billion, okay. It used to be bigger than that when they were counting options in different ways, or granting options and things like that. It was as large as 7 billion. But if you think of Microsoft Research, which is the part of Microsoft that acts exactly like a university research organization, that is, by and large, they're looking 5 or 10 years out, although some of the stuff is shorter range, just like what we do. That's 700 heads. They don't report the expenditures on that, but if you impute a loaded cost of $300K to each of those heads, it's $200 million, which is real money, okay? The entire National Science Foundation computing research budget is only about double that, right? But on the other hand, it's a couple percent of Microsoft's overall R&D budget. Now the question is, how much does Cisco spend looking more than one product cycle ahead? 0. You know, how much does Oracle spend? 0. How much does Dell spend? 0. All right, so I don't mean to criticize Microsoft for only spending a few percent looking more than one product cycle out. Rather, they're one of the few companies that's doing it these days. All right, so most industry R&D is engineering the next release of the product. Okay, and that's, for example, what you're legally allowed to take the R&D tax credit on. All right, so everybody doing advanced development is part of the R&D bucket. So lots of people at Cisco and Oracle, contribute to the company's R&D tax credit, but they're not looking more than a couple of years out. We'll talk more about program managers later. So now let me come back to this picture and point out DARPA's role. And I didn't research this, I just made it up. What I've done is to put a star by a set of things where I think anybody would agree that DARPA played the predominant role in kicking this along, all right? So time sharing, all of the early time sharing research at MIT and other places was DARPA supported. And Butler showed that as an input, sort of the Xerox PARC work. The internet, right? I'll talk in detail about that in a minute, but that was a DARPA research project launched in 1968 as ARPANET. DARPA has changed its name. It was ARPA, DARPA. It'll be back before long, I think. Right? The defense comes and goes. But the internet is clearly a DARPA technology. Modern integrated circuit design, the Meade-Conway School of Integrated Circuit Design was DARPA-funded work. Reduced instruction set processors. Obviously, IBM played a big role, but Hennessy and Patterson's programs were lavishly funded by DARPA for years. RAID disk servers. Berkeley played a huge role in RAID, but the truth is that Thinking Machines was shipping the data vault, which was a simple RAID array at the time the Berkeley project got launched, but Thinking Machines was propped up by DARPA, as well as the Berkeley work being funded by DARPA. So RAID, redundant arrays of inexpensive disks, just clearly DARPA played the predominant role. Speech. DARPA has been funding speech research since the 1960s. I'll say a word about that later as well. So those are areas where DARPA clearly did it. And now what I've done is to add in green areas where DARPA played a really major role, even though there might be some quibbling over whether they played the predominant role or not. Client-server computing, they were very large in supporting that, and both directly and indirectly. Indirectly is that all the folks at Xerox PARC who did the incredible work on distributed computing in the 1970s were in fact DARPA-supported researchers at Berkeley. Bob Taylor, when he was a DARPA program manager, had been funding those folks to do time-sharing research at Berkeley. And then when he left DARPA to run the computer systems lab at Xerox PARC, he just hired all his former DARPA-supported researchers from Berkeley. Okay, so Simone had been at Berkeley, Lamson had been at Berkeley, huge numbers of these folks had been at Berkeley. So it's just sort of, that just fed right into it. Graphics, I'll say more about that in a minute, but the National Science Foundation funded a lot of sort of the mathematical work on graphics and the graphics pipeline. But what DARPA did, I think we'll see more about this in a minute, is they funded the VLSI design program. And the goal of the VLSI design program was to get integrated circuit design out of the hands of the guys in the white bunny suits, okay, and into the hands of architects who understood sort of system level architecture as opposed to instruction set architecture or processor architecture, and make it possible for grad students to fabricate integrated circuits. Okay, so one part of the VLSI program was the creation of this outfit called Moses. It wasn't actually an outfit, it was a software capability. And here's what Moses did. You know those pictures of big wafers, and the wafers have thousands and thousands of integrated circuits on them, and when Intel does it, all of those integrated circuits are identical. Right? But if multiple people design different chips, different integrated circuits, and they use a common design language, then there's no reason for the wafer to contain 10,000 identical chips. The wafer can contain 100 for you and 100 for you and 100 for you, and you just bid it out to some fabrication facility that happens to have extra fab capacity. You pay for it. All right? And it comes out, and you slice these things up, and you wire bond them, and you mail 100 to you and 100 to you and 100 to you, and everybody has their own integrated circuits in sort of scale suitable for testing or use or turning into tie-tacks, whatever. Okay? So one outcome of the VLSI project was that Jim Clark, who was a computer graphics faculty member at Stanford, said, you know, I bet I could take this entire rack of MSI electronics that is the graphics pipeline. Graphics processors were just, you know, enormous racks in those days. I'll bet I could reduce that to a couple of integrated circuits. And that's what became SGI. Okay? So SGI is dead now because they had, again, a long story, and I'll tell it probably incorrectly, but roughly they had this incredible cash cow business in which they could charge a huge amount for something that didn't really cost that much. And they built a corporate structure based on their ability to do that. And then along come the gamers developing high-performance GPUs for gaming on Intel processors put into boxes by Dell running the Microsoft OS. Suddenly the price plummeted. One other thing that Intel did was to increase the bandwidth between the processor and the GPU. All right? So it became possible to do high-performance graphics on the sort of commodity price curve, and SGI was kind of left there with a corporate structure that demanded enormous margins. All right? But fundamentally, modern graphics comes from SGI, which came from the VLSI program. A little faster, lots of local area network research was DARPA. Workstations we've talked about. You heard about that from Butler. Graphical user interfaces. You know, DARPA, for example, was funding Doug Engelbart. I hope you looked at that video. It was a little long, but you know, you have to realize that was 1968. There were a few instances in the 60s in which people did demos or theses that, in some sense, laid out a 30 or 40-year program of research. All right? And Engelbart was one of them. Relational databases, DARPA and NSF. Parallel databases, DARPA and NSF.
And what's the parallel database?
Well, David DeWitt at the University of Wisconsin gets a lot of credit for parallel databases. So the question here is, how do you run a database on a multiprocessor? And the trick is not so much running it on a multiprocessor, it's avoiding so much software locking that you don't get any benefit. Right? So it's pretty obvious that you can run gazillions of independent transactions on a parallel database system, but it's less obvious how you can do sort of closer linked operations. So it's really not, the issue is not building the machine, although there's some aspect to that. It's designing the database and the locking so that you don't have software synchronization that keeps you from utilizing the available parallelism. Okay, so just huge DARPA impact. So now let me go back to Bonvillian's paper, which you probably read, and I'll go quickly over this. Bill Bonvillian is a guy who for decades was Lieberman's science staffer. Really, really good guy. And a year ago, MIT was clever enough during a moment of despair on Bill's part with how things were going in DC to hire him as their federal relations guy. So the paper that you read is Bill saying, hey, if we actually want to tackle green energy, okay, and energy consumption in this country, we need to mount a serious research program, and it needs to be a research program in the DARPA style. So that's basically his pitch, but he does a great job of describing the origins of DARPA and the DARPA style. And it begins with this guy, Alfred Lee Loomis, who was a Wall Street tycoon, although educated in science, but decided he wanted to make a living, who sort of post-Wall Street built essentially a private research campus called Tuxedo Park, where he collected a set of absolutely top scientists and funded them out of his personal fortune to do research. And then in World War II, and you read this, interceded essentially between the U.S. and Great Britain, who were squabbling over who would have access to what, obtained access to some British work on sort of the foundations of radar and built the MIT Radar Lab. All right, so just a phenomenal sort of individual contribution, but the most important thing in terms of model that he did was to collect absolutely top scientists, provide them all the facilities they needed and all the funding they needed, not have a gigantic management bureaucracy, which certainly every university has and most corporate research labs have. And again, Microsoft is an exception in so many regards, but most corporate R&D has just this enormous management tree with people squeezing you here and squeezing you there, so it's not much more productive than universities, okay? So that model was really effective. Vannevar Bush was Roosevelt's World War II science advisor, the director of the Office of Scientific Research and Development, and wrote this incredibly influential paper in 1945 called Science, the Endless Frontier. And essentially what Bush argued was that a set of science efforts, all right, in cryptanalysis, the atomic bomb, radar, had really saved our bacon in World War II. And the science community had been able to be mobilized to tackle these problems. And science really did have something to offer the nation in terms of security, and it should be supported by the government. It's interesting that Bush was also a computer science visionary. And he proposed this thing called the MEMEX, which everybody published their work in the Atlantic Monthly these days, by the way, okay? And this was a sort of caricature of the MEMEX, but it's a machine that we're now, 60 years later, on the verge of being able to build. It's a machine that essentially remembered everything that you saw and heard and read and organized it and made it possible for you to retrieve it. Okay? So in 1945, he envisioned this as something conceivable and sort of described its functionality in detail. And you can think of a set of things that people wrote in the late 40s as having motivated decades, 5 decades of artificial intelligence research. Right? You know, people envisioned chess, they envisioned speech, they envisioned natural language translation, they envisioned this MEMEX capability. Right? Now, things didn't actually go so well for Vannevar Bush. What he envisioned was that science would be managed by the government in an integrated way. This doesn't mean that it wouldn't be distributed. It would be distributed. It would be at industrial labs and universities, but it wouldn't be stovepiped into disciplines. Right? So, and you know, so he realized that in World War II, a huge amount of the gains had been by assembling interdisciplinary, multidisciplinary teams to tackle grand challenge problems. Right? And that's not how universities are organized. We've got a biology department and a computer science department and a statistics department. Okay? And what our buddy Loomis had done in World War II was to go out there and pluck the very best people from the multiple disciplines that he needed to tackle these problems. And that was Vannevar Bush's model for how it should go. And it didn't turn out that way. The government was slow to launch into this business. And then, of course, different government agencies were squabbling. So the result today is we have a National Science Foundation. We have research in the Defense Department. We have research in the Department of Energy. We have research in the National Institutes of Health. Every government agency has its own research organization and research funding mechanism, and different people go to different troughs, and the interesting work that lies at the intersection very seldom gets done. All right, so sort of the tragedy is that his complete model didn't get implemented. In 1957, Eisenhower established ARPA, the Advanced Research Projects Agency, the Department of Defense. So that was the defense research arm, and hired Licklider, an MIT guy, as the first head of what was called the Information Processing Technology Office. And again, IPTO has changed its letters from time to time, but that office still exists today. And here's DARPA's mission. Now, the bad news is I can't get the historical documents, and people get to rewrite this. So what it says is DARPA's mission is to maintain the technological superiority of the military and prevent technological surprise from harming our national security by sponsoring revolutionary high-payoff research that bridges the gap between fundamental discoveries and their military use. The truth is that this bridges the gap part is a sort of modern addition. All right? This is the traditional mission of DARPA, and we'll see how they've carried that mission out. I'm just going to give you a set of examples of what DARPA has contributed. For example, stealth is a DARPA technology, right? And you know, the vision was aircraft and also ships. They've done stealth ships that can't be detected by radar, right? And this is a legitimate multidisciplinary problem. It's engine technology, it's aerodynamics, it's composites to build the aircraft out of, it's electronics. A huge number of contributions were necessary in order to pull this together. What DARPA does is to mount a program that says we want stealth aircraft, and we're going to need this, and we're going to need that, and we're going to need that. The grand challenge is stealth, and we're going to assemble the research teams to do the work that in 5 or 10 or 15 years is going to yield stealth. All right, so DARPA research fed directly into every aspect of stealth. Similarly, infrared sensors. DARPA's goal was the military phrase, it's in this, own the night. All right, so give American military forces a capability that they didn't have and that nobody else had, which is night vision, right? And make it portable, lightweight, cool enough in terms of its operation that can be deployed on tanks and armored personnel carriers and in aircraft and on individuals. Okay, so again, that's a DARPA capability, truly interdisciplinary. The military has it. No other military has it. DARPA gave it to the military. DARPA gave us unmanned undersea vehicles. You can understand why the Navy wants those, but the entire oceanographic community is driven by these things. Okay, they call them AUVs, autonomous undersea vehicles, and they cruise Monterey Bay and they cruise Puget Sound taking samples. And what's interesting about many of the ones that the oceanographic community uses these days is they're not powered, or rather they have a small amount of battery power. So what these oceanography AUVs do is they have a bladder that can be compressed and expanded to affect their buoyancy, right? And they simply porpoise, right? That is, they come to the surface and telemeter scientific data back to a satellite, right? And then they dive, change their buoyancy and dive. Okay? That gives them momentum, which gives them control, right? They get down to the bottom. They even sometimes go to the bottom and use acoustic modems to collect data from instruments on the ocean floor, in addition to their own instruments. They then surface, and again, that's creating momentum, right? Get back up at the surface, telemeter their data, dive again, right? You don't want to deploy nuclear power plants for sort of general scientific use in the sea. So this is a way to have these things. They sometimes go to sea for months at a time with modest amounts of battery power just porpoising along. Okay? But again, DARPA technology. Phased array radars, DARPA technology. Unmanned air vehicles. So you've seen these big time in Iraq in recent years, but again, that's a DARPA technology. And the armed forces did not like this at all. At least the Air Force didn't, and the Navy didn't. Why? Because pilots are, the top guns, right? This is, it's sort of a throwback to how in the 50s and 60s the test pilots wanted no part of NASA, right? If you've seen these, what's the name of the movie? I've forgotten.
Right Stuff.
Right Stuff, yeah, okay? These real test pilots just viewed the NASA astronauts, they called them monkeys, right? And indeed, Ham, the chimpanzee, was the first thing set up there, okay? So The test pilot's view was these were pretty boys who strapped themselves to the front of a rocket and went along for a ride for PR purposes. All right? And so, similarly, there are aspects of the military that were none too positively disposed towards this capability. But DARPA developed it, and it's incredibly widely used today. Ceramic materials for bulletproofing and things like that, DARPA. I could go on and on, I'll stop. But this is the sort of stuff that DARPA does, yeah.
Was the Star Wars program also DARPA funded?
That's a great question. And
it had its own office.
It had its own office.
Okay.
Yeah. And Star Wars was very controversial in the computer science community. I think there were a set of people who believed that this was dangerously unlikely to be realizable.
Controversial, too, in the physics community.
Great. Okay. So let me talk about the internet for a second, and this will just sort of show you the history of this and the DARPA involvement, and then I'll talk about one program manager in DARPA, and then I'll be done, although I see I'm already over time. So in 1966, there were the very first experiments in digital packet switch technology in Britain and elsewhere. In 1968, ARPA issued a request for quotations to build these things called IMPs, which are interface message processors. So those were the nodes on the ARPANET. In 1968, there was, of course, no national backbone network, but there also weren't any local area networks. ARPANET was inaugurated in 1969 with 4 hosts. Okay, they were UCLA, SRI,
Utah.
and Utah and Santa Barbara, I think, were the 4 original hosts. All right, the very first message over ARPANET was Len Kleinrock's programmer at UCLA trying to remotely log in to an SRI Sigma machine. This is the company SDS, Sigma Data Scientific, was bought by Xerox. That became Xerox Data Systems. It was one of those disastrous acquisitions that Butler talked about from a Sigma 7 at UCLA. And in contrast to whatever it was, Watson, come here, I need you, the first message sent over the internet was LO, because Charlie was trying to log in at the remote machine and the whole thing crashed after he typed the O. That's the first recorded message on the ARPANET. This is Charlie's log from the 29th of October in 1969 on Len Kleinrock's website. In 75, ARPANET had 100 hosts. And you know the exponential growth thing, of course. Let me just say that what ARPANET was then was a set of IMPs. I'll describe these in a sec. Connected together by telephone lines and essentially modems. Okay, so until long after 1975, the bandwidth of ARPANET was, ready for this, 56 kilobits per second. Okay, 56 kbs was the bandwidth of the national network, and each of these IMPs was the size of a rack today. I mean, it was a rack. Okay, and the IMP, the interface message processor, essentially took packets off the ARPANET and sent it to up to 4 hosts. So there were no local area networks, but depending on the configuration of your IMP, you could have up to 4 computers on it. And those computers were time-sharing computers. And the only applications on ARPANET in the 70s and the early 1980s were, first of all, Telnet, which is remote login. Okay, allowed you to log into a remote machine. Secondly, FTP, which allowed you to send a file. And third, email. That was it. Okay, so remote login, file transfer, and email. Right? And you could indeed send, any user on any one of these machines could send email to any user on any of these other machines, but these 100 hosts were entirely military sites and major universities with DARPA contracts. Okay, so it was a military and military contractor network. In 1977, there was an experiment with internetworking, and the Xerox folks participated in this, and it involved a computer driving along 101 in the back of a truck, okay, sending packets by radio, right, to, I believe, Xerox. It went over ARPANET across the country to a satellite network. Okay, there's a packet radio network coming out of the truck. Okay, it was a satellite network to England. and down to a computer there. Okay, so we had a very crufty, cobbled together version of internet working in 1977, again sponsored by DARPA. In 1980, the design of TCP/IP was completed. So here's what's important. Prior to 1980, or at least prior to this experiment, there was no such thing as internetworking because the world had exactly one network, and it was this guy. Right? So it was a set of computers hooked to the ARPANET through IMPs. So an internet allows you to route packets from network to network to network. Right? In the ARPANET, there was only one network, and every IMP had routing tables. So if you wanted to get from Washington to MIT, the IMP knew exactly how to send it, and the packet format never changed. The packet format simply traveled on ARPANET links. Right? Your host, we had a DEC System 20, and the DEC System 20 jacked into our IMP. Right? Over a custom interface built for the DEC System 20. Right? And the IMP took essentially characters from the DEC 20, packetized them, and shipped them across ARPANET. Yeah, question?
So that was all hard-coded, like the somewhat dirty host at Park?
Let's see. Hard-coded is not quite right, but almost. Every IMP had a complete set of host tables, and those were updated by massive downloads periodically.
But it was meant to be scalable from the start, or?
Well, so computer science is time after time after time, somebody writes a paper saying, I've designed a scalable system. It can be a network, it can be a file system, it can be anything, okay? Then the next paper is, I've built this scalable system and it works, it's really cool, and here's some performance numbers. And paper number 3 is, oh my God, I missed a few things. All right? And Carnegie Mellon, for example, has sequences of these 3 papers on scalable file systems. Xerox has a set of great papers on Grapevine, which was their scalable mail system. Okay? And they just missed some stuff. You never anticipate at all. What the folks at Google say is they try to plan for 2 decimal orders of magnitude of scalability, and then they plan to throw it away. Right? Because there's just a sort of legacy of us being completely incapable of predicting more than 2 decimal orders of magnitude out. Right? We get hit by the gotchas. So what Google does is to try very hard to get 2 orders of magnitude right, and then just scrap the sucker and start again. That's undoubtedly not that clean, but that's roughly what happened. So was it supposed to be scalable? Yeah. Was it really scalable? No way. I mean, in the Ethernet was deployed in Xerox around this time, the late 1970s, and my high school buddy David Boggs he himself was in charge of giving out hardware Ethernet addresses. That's not very scalable, right? You wanted an Ethernet address for a new Ethernet interface, you'd call Boggs and he'd give you a number or a range of numbers. Yeah.
DNS is an exception, right? Because it has kind of stood the test of time and has scaled with
Yes, but we haven't quite got to TCP/IP yet. So you're absolutely right, okay? The scalability of the internet is utterly remarkable. It's scaled over many decimal orders of magnitude with very modest changes to these original protocols. Okay? So TCP/IP, the design began in the late 70s. It was completed in 1980. Vint Cerf and Bob Kahn did this, and they received the Turing Award and everything else for this. Remember that they didn't do packet switch networking. So the folks who did packet switch networking are perhaps justifiably a little grumpy that Bob and Vint are the internet people, but in many ways I think the internet is the TCP/IP protocol, right? And so remember that what IP does is route packets from network to network to network to network, and what TCP does is take a long message and break it up into multiple packets and make sure that each of those packets gets to its destination and deal with packet loss and out-of-sequence arrival and stuff like that. Okay? And in fact, in Vint and Bob's original design, TCP and IP were one protocol, and it was subsequently split apart. Okay? Then, in 1983, there was this unbelievable day, I remember it here, in which, and there were about 500 hosts on the internet then, okay, which you should think of as basically as 500 hosts connected to IMPs, because although we did have Ethernets, you couldn't really route internet packets over them. Okay, there was this day in which everybody had to switch from the previous protocol to TCP/IP, right? And if you didn't switch, you were SOL, right? So 500 hosts was probably, I don't know, I'll make it up, 250 sites. We had a couple computers. Some people had as many, 4 computers, right? So the 200 or so site administrators agreed that on this particular day, they were all going to change over to this new software. And everybody did it. Lo and behold, it worked. And with, in some sense, stunningly minor modifications, we've been running this thing for 23 years now. Utterly amazing. Okay? In 1988, ARPA got out of the networking business. This was transition technology, so the National Science Foundation took it over. Up to 88, it still was the case that only DARPA contractors and a few rare other people were on ARPANET. It wasn't super large until NSFNet took it over, although the number of hosts was way up because we now had internet routing and local area networks and workstations. All right? Backbone speed still in 1988 was 56 kilobits per second, modem speed. All right? 1989, I mentioned this last week, Vint Cerf got permission to interconnect MCI mail to the internet. All right, so previous to that, if you had MCI mail, you had an account on a time-sharing system somewhere, probably in Northern Virginia, and there was a modem pool in every major city, and you called the modem pool and connected to the time-sharing system, and you could exchange email with anybody else whose email account was on MCI mail, and nobody else. All right, so back to Ray Ozzie last week. You know, that's the story of why, one reason why corporate email took so long to get traction. It just didn't exist. 1990, backbone speed increased, lots more hosts. 1992, National Center for Supercomputing Applications did Mosaic, which really triggered the growth of the web. Okay, so as you know, the web was actually put together by Tim Berners-Lee, working at CERN, the European physics community, but it was a sort of text interface. So what happened was an undergraduate student working at NCSA did the Mosaic browser just as a flyer. And in some sense, it's this enormous success of National Science Foundation funding, but this was a kid taking a flyer. Mark Andressen, yeah.
Interesting. The side there is that it fit on a single floppy.
Yeah. Okay. Today, more than 400 million hosts. Utterly unbelievable. And the research community today is launching an initiative to build an infrastructure to let us try and actually re-envision the internet. All right? So what this means is these protocols, which have stretched for many, many decimal orders of magnitude and 25 years, are just not stretching any further. I think anybody can be convinced of the elevator speech, which is it's not secure, it's not reliable, it's certainly not scalable to the point that every device in your home can have an IP address and communicate. It's not manageable. The question is, what's next? And you can't run experiments on what we got at the networking level. Yeah, question.
Comment. Mosaic might have fit on a floppy, but a lot of us Lynx users are still awfully sore about the way that graphics have slowed down the net. I could have gotten anything in Lynx in seconds. All this picture stuff and JavaScript just brings it to its knees.
Yeah, but, you know, Aunt Martha isn't going to use Lynx. That's the problem. And the bad news is the web is for Aunt Martha.
Question from San Diego.
Yeah.
Speaking of the web being for Aunt Martha, how do you assess the outcome of the ARPANET and internet development in terms of DARPA's mission?
Right. So that's a good question. You know, the entire sort of military approach these days is what they call network-centric warfare. So they have bought into this hook, line, and sinker. The bad news is that there's no way to state this politely. The research community, let me put it this way. I had a friend 10 years ago who took over as chair of the computer science department at Princeton. And he called me a couple of weeks later after his first meeting with the provost trying to get more money. And what he said about his predecessor was he used up all our superlatives. right? That is, he's already made all these extravagant claims that were as yet unfulfilled and had taken the money for them. So there was nothing left you could promise to get more money. So in some sense, the networking research community has done that with DARPA, right? Which is they have funded all kinds of research programs to give them secure networking, which we ain't really got. Right? So I think a problem is that the whole sort of doctrine of network-centric warfare relies on a set of capabilities that we really haven't delivered. They don't have any greater ease deploying battlefield networks than you do making your wireless work in your home. Right? And they don't have significantly better security in those environments than we have. 85% of the hardware and software that went to Iraq was drop shipped from Dell and Cisco and Microsoft. Right? So by and large, the military is running the same stuff we've got, so they got the same problems we've got. Right? So I think in terms of how it's changed the way the military does business, it's been a phenomenal success. In terms of the capabilities it actually delivers that the military thinks it needs, it falls far short, and that's our fault for claiming but not delivering. Yeah.
But it's almost kind of ironic that civilian security requirements are pretty close in some ways to military, because there's a lot of money being involved right now with the
right. So in some sense, the good news is the military is once again going to benefit from COTS. All right, from sort of the PC multiplicative factor and cost curve. Absolutely right. Everybody needs similar levels of security these days. So I'm running way over. Let me try and scoot through this. This is a list of DARPA program managers, and without casting aspersions on this side, let me simply say that the people on this side are great people in computer science. Okay, so these are the people who ran the Information Processing Technology Office, or the Information Technology Office. So the structure of DARPA is they don't do any research, they just manage and fund research. There's a DARPA director, and then there are, depending on the day and the week, between 5 and 8 offices. And each of those offices has a director, and then those offices have a set of programs, and each of those programs has a program manager. Right? So DARPA is a couple hundred people, and IPTO is one of those 5 to 8 offices, right? Licklider, Sutherland, Taylor, Roberts, Licklider again, Bob Kahn, Amaral Schwartz. These are great computer scientists and visionaries who caused utterly amazing things to happen from 1960 to 1990. Utterly amazing things. So let me talk about how Bob Kahn ran IPTO, and Bob had a bit of an advantage. So this is the TCP/IP Bob Kahn, right? But he ran IPTO for 6 years from 1979 to 1985. An advantage that he had, which he'll admit, is that he was a program manager in IPTO prior to this. So he knew the ropes and was well entrenched and had a set of programs going, right? But what you'll see is the way DARPA can do business, and the National Science Foundation can't do business these days. NSF proposals come in over the transom, they're peer-reviewed. You fund the best ones, but you don't have these sort of grand challenge visions typically that get big cross-disciplinary segments of the research community working on things. So this will be quick because I've already talked about this. Kahn did the VLSI program, integrated circuit program, and one thing that came out of that was the Meade-Conway design methodology. This was to design integrated circuits by writing programs. Okay, we wrote programs originally, believe it or not, in Simula 67. And roughly what you would do is, remember, eventually in an integrated circuit, you have to wind up with a circuit plot in 4 levels. Red, green, black, and yellow are the 4 colors you'd use, and those are the different layers of an integrated circuit. And so you would design the transistors, but what you do is design a single bit slice of a register, and then in a loop, and design means literally write the program that would cause the HP plotter to produce those colors, okay? Which eventually was used to produce the integrated circuit masks, the 4 masks you needed. And then you would just put that program in a loop, and you'd have a 32-bit register. All right, so this sort of hierarchical design done by programming instead of by putting tape on big pieces of mylar, which is how it had been done. And then Moses, which I've described, a fabrication methodology that developed this thing we called a multi-project chip, a single chip wafer that had a couple hundred instances of a couple hundred different integrated circuits on it because everybody was using the same programming language. Right? Then he funded Berkeley Unix. And Berkeley Unix was, in many ways, pretty boring. It was take Bell Labs Unix and put virtual memory in it. But the reason he did that was the integrated circuit designs needed more memory than you could afford to buy. Okay, these were big programs, big designs you were doing, and so they needed virtual memory on Unix, and the image understanding program, which they were also doing at the time, needed big address space for large images. But Berkeley Unix was also a Trojan horse for TCP/IP. So if you scroll back to the early 80s, every company had their own networking standard. This lasted until the late 80s, right? IBM had SNA. Microsoft, God help us, had LAN-MAN. Novell had some stuff they acquired from Xerox. There was DECnet. There was AppleTalk. There was TCP/IP. These were all completely incompatible protocols. In the 80s, Cisco would build network routers that would route 5 and 6 different protocols. It was complete craziness, right? And Europe went their own way with X.25, a complete disaster. The good news is they drove a standard. The bad news is it was kind of the wrong one. It set them way back, right? But notice that Europe did very well in digital cell phones, right? There they picked a standard that the whole rest of the world uses, and the U.S. has 4 standards, right? And the result is one cell phone works everywhere in the entire world except in the United States. All right, and you plug in these SIM cards in and out. Okay, so Berkeley Unix also had TCP/IP, and it got it deployed throughout the university research community. All right, so it was a Trojan horse for the widespread adoption of TCP/IP and a common platform for system and applications research. Okay, then he did the Sun workstation. The reason was integrated circuit designs needed good graphics. Forrest Baskett, who was a faculty member at Stanford at the time, convinced Kahn that no existing workstation, again, this is the very early 1980s, so there was no Apollo. Apollo was the first workstation with a bitmap display. There was no workstation. There was no Sun workstation back then, okay? So Sun stood for Stanford University Network, okay? So Bechtolsheim, Andy Bechtolsheim, was Baskett's grad student. Bechtolsheim had this cool design for a frame buffer. So Kahn said, go ahead and build this damned workstation so you can do your integrated circuit design, but I'll only fund the project if you run Berkeley Unix. All right, so he's tying all these things together by mandate. There was lots more of this, but the clear byproducts of this, aside from a bunch of capabilities, are Sun, SGI, I already mentioned Jim Clark, reduced instruction set computers, which Hennessy and Patterson did as part of the VLSI program, the adoption of TCP/IP, internet routers by Cisco and 3Com. Okay, that was just what Stanford did, was to take Sun boards with 68,000 microprocessors on them. Let me back up a bit. The way we did internet routing, okay, prior to internet routers, was your VAC 780 had routing software on it and multiple Ethernet cards in it. Okay, so your time-shared computer was also a router, right? And that, again, wasn't very scalable. For Stanford's campus network, what they did was take a bunch of these Sun 68,000 boards, put Unix on them, right, and make them nothing but routers, or alternatively terminal servers, little boxes that sat there and had multiple Ethernet cards and routed from network to network, or multiple terminal ports and multiplexed the terminals onto the network, okay? And that really became Cisco and 3Com. In the case of Cisco, I don't know 3Com story. In the case of Cisco, a couple of people just basically walked out with this and created the company. Right? So that's really the picture. Graphics, the internet, local area networks, workstations, integrated circuit design, RISC processors, all out of Kahn's program at DARPA. Unbelievable. So that's what this agency does. I'm practically done. DARPA is a mission agency. Okay? So they don't support all of computer science. What they do is support the computer science that's going to give them capabilities they think the military needs. Okay? So, as one last example, DARPA sponsored the vast majority of research in speech and natural language for decades. And what were they trying to do? Well, in Iraq, for example, soldiers have this little device called a phraselator. And here's what a phraselator does. It's real simple speech recognition. It has a couple hundred phrases in it. And you shout a phrase into it in English. and it figures out, this has to be one of its several hundred pre-canned phrases, okay? And it barks that phrase out a 2-watt loudspeaker in whatever the local language is, right? Now, presumably, I mean, this thing doesn't translate, okay? So this command has to be something that doesn't require a verbal response, like stop or I'll shoot you, or how many people are in that building, right? But it's an incredibly useful capability, fairly straightforward speech technique. The company that did this produced it in an incredibly short period of time based on 20 years of speech research. Another example, again in Iraq, is there are a set of systems that the military uses to monitor public domain documents such as news clippings from towns around the country. And here's what it does. It's pretty primitive translation and natural language understanding and binning. So what Tides and Ears do is identify the 5% of the documents that some human being should do a competent translation of. Right? So nobody actually uses the Tides and Ears translation. It's not that good, but it's good enough to find out if this is, a report on the town picnic, okay, or if it's something that the U.S. military should be interested in. So again, great capability. You can think of it as a multiplicative factor of 20 for the small number of people over there who know the language directly out of DARPA technology. This is again from Von Villian's paper. We've covered all this. Small agency, flexible, only 3 levels in the hierarchy, very little bureaucracy. Technical staff is really outsourced to universities and labs. For example, SRI is a huge DARPA contractor. BBN is a big DARPA contractor. It's not just universities. They build teams and networks of teams, and they force them to work together and use each other's stuff. Organized around this Grand Challenge model. The DARPA Grand Challenge last summer with these robot vehicles in the desert is a great example. Again, that was a great engineering effort building on 15 years of research, right, in sensors and things like that. Okay, and what's interesting is of the 5 teams that completed the Grand Challenge, one, as I understand it, was basically a bunch of guys from a garage in like Louisiana or something like that. Okay, the other 4 were university teams, right? So they picked the robot vehicle specifically because lots of the technology that you needed was available off the shelf. For example, in order to accommodate the disabled community, you can get all kinds of interfaces to cars that control the steering, control the throttle, control the brakes. You didn't have to invent that stuff or build it. You can buy it because it's adaptive technology that's standard for cars. You can buy the sensors. The better funded teams had more better sensors, but fundamentally anybody could buy this stuff. Outsourced support, great program managers traditionally, these networks of collaborators. That's the story. Yeah, Marty.
I'll just give you a quick funny story. Sometimes you get lucky by accident. And I was at Lockheed at the time, and Ben Rich, who ran the Skunk Works facility, wrote in his book this great story of the government funded a bunch of contractors to go out and look at stealth technology. Lockheed was one of them. They were pounding their head against the wall trying to figure out the best way to approach this problem. For sheer luck, one of the engineers liked to read open literature, Russian scientific papers. And it turns out there was a really brilliant physicist over in Russia who had done all this work about stealth technology and about how fastening metal would work. But the Russians never used this, never capitalized on it. And that ended up forming the core technology that Lockheed
For
used
stealth. Great.
on how to build stealth aircraft.
Very interesting. Is there another question here? Yeah.
So what kind of funding has DARPA had over the years?
DARPA's funding these days is a couple $2 billion. So it's a pretty significant level of funding.
But has it gone up and down with different administrations, or has it been pretty steady?
I should have a graph. I don't. It's gone, so you, of course, have to calibrate this for inflation. Okay, so if you calibrate it for inflation, it's been, I would say, relatively steady with some ups and downs. There are, something I haven't got into is that there are, if you read the New York Times, you will see that the computer science community in particular has some differences with the current director, right? And I would say that by and large that stems from the fact that many research programs are getting classified, which means foreign nationals can't participate. Universities don't do classified research. There are a lot of programs that have sort of 12-month go, no-go decisions rather than long horizons, and it seems very difficult to pick winners and losers after 12 months. And if part of what you're doing in a university with a DARPA contract is supporting grad students, you can't, after 12 months, say to the students, sorry, that's not your thesis anymore, it's over here.
Is that a reflection of the Bush administration, or just the particular person in charge?
I suspect a combination of ingredients. You know, there was a squib in a John Markoff article this morning about the DARPA high-performance computing program, pointing out that the current DARPA director was a good buddy of Rumsfeld, and there was some talk that he might be heading off to greener pastures now that Don has been sent packing. But I have no idea. I'd rather not speculate on tape, okay? But I think there are a set of issues, and computer science is in many ways the canary in the coal mine. That is, the characteristics I've described are affecting all fields. But because DARPA has been so important to computer science, we felt it, okay? And what we observed was that at places like Stanford and Carnegie Mellon, MIT and Berkeley, DARPA funding has dropped by half in the past 4 or 5 years in computer science. And at MIT, DARPA funding overall, not just in computer science, has dropped by a factor of 3. So it's not just affecting computer science. And that's not a conscious objective of defunding universities. It's a set of policy changes that cause universities not to participate. A result for the field, and I'll then get off this jag, is about 6 years ago in the Clinton administration, had to be longer than that now, 8 years ago, there was a significant ramp up of funding for computing research, the bulk of which went to the National Science Foundation. But this coincided with DARPA's change in character, okay? So what's happened, in fact, is that funding for the field has not gone up by nearly as much as the graphs show or is intended, okay? Because the major DARPA-funded organizations, major universities, for example, simply offset their decrease in DARPA funding with increases in National Science Foundation funding. So the net increment is much less than appears. So it's been a problem for the field, yeah.
Could it be that like even internet started like a classified project, right? Only military wasn't allowed to connect. So whatever they have right now eventually will come to public domain. Right?
Well, let me say a couple of things. One is that the ARPANET research was not classified at all. It was completely open, okay? So only defense contractors could attach, but there was nothing secret about the protocols. I mean, Surf and Con published TCP/IP, and all the stuff before that, all the packet switching was published. Secondly, if DARPA classifies its cybersecurity research programs, which they have. All the new starts in cybersecurity have been classified in recent years. That has the following effects. One is university researchers can't participate. A second is students don't get trained. A third is the military runs on the civilian networking infrastructure. They buy their stuff from Cisco just like we do, okay? And also all the rest of the nation's critical infrastructure, the banking system, telecommunications system, run on this commercial infrastructure, and classified research doesn't impact the commercial infrastructure. So one could argue this isn't even the right thing for defense because 85% of the gear that went to Iraq was drop shipped from commercial manufacturers, okay? But even if it is the right thing for defense, it's not the right thing for the nation as a whole. And because this administration doesn't give a rip about science in general, all right, there's been no backfilling and no coordination, okay? So if DARPA is not funding fundamental research in civilian cybersecurity, somebody else ought to be doing it, but nobody else is. You know, we all know the story of DHS, for example. You know, this might be their job, but they're doing nothing. Any Microsoft questions? Perfect. Quickly. Sorry. Go ahead.
So something interesting, and this is probably the only place where it's going to fit, is that we haven't really talked about in class is the role that international students or people have played in history of computing.
Yep.
And I don't know, at least around here at Microsoft, I see like half the people are from other countries, right? So I think it would be interesting to talk about.
Right. So I'm on a new National Academy study, which among other things is looking at exactly that. One of the guys who's co-chairing the study is Eric Benamou from 3Com. And Eric, like many people, is a guy who obtained, he's a French national, obtained some of his education in France, some of his education in the United States, has been a serial entrepreneur with many, many, many billion-dollar companies. And, you know, what Eric provides us with is these lists of entrepreneurs who are immigrants to this country. So Yeah, I mean, that's another problem with this administration is its immigration policy. Right, we could spend a whole night on this, but let's just, hope for regime change. You're absolutely right. We didn't cover this, but at Microsoft and every other tech company and in the Bay Area, I mean, you probably see at Microsoft this group called the Indus Entrepreneurs, which is sort of entrepreneurial East Indians, is an enormous and important group in the Bay Area, in Seattle, and elsewhere. It's just sort of this self-reinforcing crew of people. In Seattle, they're mostly ex-Microsofties out there starting new companies.
Question from Berkeley.
Yeah, Berkeley.
Have there been any like major failures that you can point to in terms of DARPA? Any bets that really just didn't pan out?
Yeah, and I think the general story is if you're not failing, you're not being risky enough. I think a great example is that artificial intelligence has in many ways overclaimed and underdelivered. Okay, and there was a thing a decade ago called the AI winter. And the AI winter was a dramatic withdrawal of funding from artificial intelligence because it was perceived of as having just made these extravagant claims they hadn't produced on. Now, that's not quite fair. One of the things with artificial intelligence is as soon as it works, it becomes systems. All right? It's like no longer AI. Okay? So another problem that AI has is we all watch these sci-fi movies, and their robots are never as cool as the ones in the movies. All right? So I think this isn't quite fair, but the fact is that in the 50s, people said speech understanding and natural language understanding and translation were right around the corner, and 50 years later, we still don't have them in a usable form. I mean, you would use Dragon Talk if you were incredibly RSI impaired, but short of that, not going to do it. As an example. So I think there have been a set of things that have panned out much more slowly than anticipated. I'm less good at thinking of monumental failures, although I'm sure there have been some. Yeah, Microsoft.
Comment on that. When I play Doom, I don't get a real gun. Artificial intelligence, yeah, it'd be nice to have a computer that can translate things for me. But just like the phrase later, Microsoft's KB articles for a couple of years have been automatically translated into Spanish. Now they're being translated into other languages. And the acceptance rate is in the 90% of people saying, native Spanish speakers saying, this Spanish translation is better, more comprehensible to me than the original English.
What I would say is, I could never make any use of this crap even when it was in English, so it's probably no worse than whatever language it gets. but no, you're absolutely right. I mean, there have been a huge collection of successes, and speech does work. If there are sort of three dimensions of speech as an example. There is how fast you're talking, there's how broad is the domain of discourse, and there's whether it's speaker independent or not. Right? And these days, if you're willing to give up only one of those, you can do pretty well. Right? If you're willing to talk slowly, it's okay. I mean, it's made huge progress. Natural language, as you said, has made huge progress. Robotics has made huge progress. Okay? There's a bunch of these promises are about to be fulfilled. They just haven't been fulfilled on the schedule that we claimed. Do you have a question? Yeah.
Just in the overall issue of incentives, would everything that DARPA does fall into the prizes category? We've talked about patents and prizes.
No, that's a great question. No, the grand challenge is the only thing I can recall that they've done that's prize-based. Fundamentally, they give not grants, contracts. Okay, there are sort of measurable deliverables, and you're managed and things like that. But the grand challenge, I would argue, didn't get research done. It got incredibly advanced systems engineering done to integrate a set of things that research had created. But Steve is a big fan of prizes as a mode of funding these sorts of things, and it seems pretty reasonable that government agencies should start trying to do that more. Any San Diego questions?
One more Berkeley.
One from Berkeley. Okay.
Yeah. So it's very striking that you tell this story about it's the 1990s and all these smart people come to NAS and not quite sure what the next new thing is. And if you'd done that in 1960, would people have come up with the Licklider list? Was there a greater sense of what you would do next in the field? because it's very striking that you have this odd pattern where everybody after 1990 is, well, just average instead of excellent running DARPA. And is that something to do with us running out of sort of the pipeline of the ideas that we started off this business with?
Well, that's one possible explanation. There's probably something to it. Another could be that DARPA behavior shifted and great people didn't want to go work there anymore. So let me just say that something happened to DARPA in around 1990, and we were a beneficiary of it, is that the way DARPA used to operate is they would give enormous block grants to a small number of places. So in computer science in the beginning, it was Stanford, MIT, Carnegie Mellon, the University of Utah, a few other places, okay? And so it's so important to note that Stanford and Carnegie Mellon and MIT did something that Utah didn't, because they sustained this excellence, all right? Berkeley got on the big-time DARPA computer science funding bandwagon later than the other three, but utilized it exceedingly well. In the 1990s, or early 1990s, DARPA got democratized, all right? So they could no longer give a block grant to MIT or a block grant to ISI, okay? Rather, they were more in the business of funding individual investigators, and it made it much harder to mount these big efforts. All right, so one of the important things for this field is that historically, DARPA and NSF had very different models. In DARPA, a program manager had an enormous amount of autonomy, and there was none of this peer review stuff. So to some extent, that meant your cronies got the money, right? And maybe it was or wasn't the best, right? And the flip side with peer review is the scientific community gets to decide who gets the money. It's typically much smaller amounts of money. It's not coordinated at all. And peer review is unbelievably conservative, right? And as money gets tighter, it becomes more conservative. You only propose stuff you've already done. You haven't told people you've done it. But the way to get the next grant is to propose for this grant what you actually did on the last grant, so that you can immediately write a bunch of papers and show that as progress, because you have to be back at the trough in another 18 months. Right? So these two models of funding have served the field very well, and DARPA moved away from this big block grant, lots of autonomy for the program manager and office director model. And I think that's partly responsible.
Question from San Diego.
Yeah, San Diego.
What effect did the end of the Cold War have on DARPA?
Let's see. It obviously had a big effect on the military. I don't think it adversely affected DARPA funding that much, so I'm just not sure. Jeff, do you know?
No, I can't say.
I should know the answer, but I don't. Sorry. Any more questions down there?
Yeah.
Yeah, go ahead.
Just going back to the language of the mission, it strikes me that certainly a lot of these projects, and I'm thinking of the internet, especially, have generated technology that is useful to the military. But I don't know if it's necessarily the case that. I'm wondering if also possibly from a technological surprise aspect, couldn't some of the technological surprise sort of not have any clear implications for or against national security, but sort of unpredictable consequences for it, maybe?
Yeah, that's undoubtedly right. And by the way, the argument for DARPA classifying its cybersecurity research is a perfectly fine argument. What they say is, this is both an offensive weapon and needs to be defended, and we can't let our adversaries know what we know about it. All right, so that's the argument for that classification. So I think, you're absolutely right. The question for all of these things, and it's hard to reconstruct history, is to what extent was DARPA trying to develop a military capability, and to what extent was it trying to do something that, in their phrase, is dual use? So for a decade, a big shtick in DARPA was dual use. That is, military use and civilian use. That's a phrase that goes in and out of favor. It's somewhat out of favor today. But clearly, many of these were dual use technologies. In the case of something like stealth, it's absolutely clear, or sort of night vision, that while there are commercial applications, at least for night vision, it's clear that that was a military capability they were setting out to develop. In the case of ARPANET, I think it's less clear that that they thought of that purely as a military capability. I'm going to guess you would get different opinions from different people who were in charge back then. Anybody else?
Question from UCSD.
Okay, UCSD, and then let's be the last one. I've blown the budget terribly. Yeah.
This has to do with military-sponsored research laboratories.
Yeah.
And predominantly in the past, they did more research than today. Do you know a reason for that?
Well, I think that our general opinion of DARPA and defense as a whole is that the horizon of what they're willing to invest in has shortened enormously in the past 6 years. Right? Now, one can argue that we're in a war now. On the other hand, all that ARPANET stuff was funded during the Vietnamese War. Right? So it's not clear that that's the answer. But I think, and let me say that Dr. Tether would dispute what I'm saying vehemently. Okay? But this whole notion of bridging the gap, what DARPA means by, what Dr. Tether means by bridging the gap is that there is I'm going to scribble on Kate's slide here. He draws a picture that looks like this, in which this is fundamental research, okay, and this is deployable technology, DT, right? And there's this gap between fundamental research and deployable technology, and that's where DARPA is, right? I think it's pretty easy to argue that DARPA used to be down here, although as well, that is spanning this entire spectrum, except that, again, like most computer science research, it's not what the physicists would call curiosity-driven research, right? Most people who are doing computer science instead of, say, mathematics are doing it because they're motivated by solving some particular problem, right? And the problems that DARPA is motivated to solve are defense problems, just like the problems NIH is motivated to solve are health problems, right? But my argument would be that in the good old days, DARPA used to start down here, although always in pursuit of some strategic objective. And now they definitely are here.
So you think that there's this national gap in basic research funding?
Let's see. Again, I don't want to spend too much time on this, but if you were to graph, sorry to do this to your slide, Kate, I'll erase it again. If you were to graph the research investments for all federal agencies on the same axis as the National Institutes of Health over the past 30 years, what you would see is that and this. Okay? So NIH's budget is now something like $35 billion a year. The National Science Foundation computing research budget is $400 million or something like that. DARPA's entire budget is a couple billion. Their computing research budget is hundreds of millions. Okay? So what's happened is, the way I would put this from a congressional point of view is if you're dealing with the diseases of 70-year-old white males, you got an ear in Congress. Okay? So there we are. Most of this money is not going into breast cancer. I can assure you of that. All right? So this is not to say that we're spending too much on biomedical research. It's to say that the portfolio has gotten pretty badly unbalanced. Okay, having blown it terribly, let me suggest that we take a break and that Kate is going to start in 9.5 minutes at 8 o'clock. All right? Thanks, everybody.